Today we are walking through the paper titled Adam's Law Textual Frequency Law on Large Language Models.
Give me the big picture first. What is this paper trying to prove?
The main claim is simple. If two prompts or training examples mean the same thing, the version written with more frequent wording is usually easier for a large language model to handle. The paper turns that idea into a prompting rule, a better frequency estimator, and a curriculum for fine-tuning.
What was missing in earlier work?
Earlier work already showed the hints. Larger models tend to handle rare words better, and small wording changes can swing prompt quality a lot. But those results did not give a general law about textual frequency itself. So this paper tries to connect wording frequency to model loss and downstream task performance.
Then what exactly is textual frequency law?
Textual frequency law, or TFL, says that when several paraphrases keep the same meaning, we should prefer the one with the highest sentence level frequency. For prompting, that means asking the model with the more common wording. For fine-tuning, it means using the more frequent input variant together with the same target output.
How do they estimate frequency if model training corpora are hidden?
They start with an approximation from public text resources. The paper estimates sentence frequency from word frequencies, so it does not need the actual pre-training corpus. That estimate is imperfect, but it is enough to rank alternative phrasings and decide which version looks more common. This diagram shows the overall method.
Walk me through the 3 stages in that diagram.
At the top, the system starts from one question or instruction. In the middle, it rewrites that text into paraphrases and estimates which version is more frequent. At the bottom, it keeps the higher frequency version because the paper expects that phrasing to give better accuracy. The caption also points out an important risk: paraphrasing can rift in meaning, so human filtering is part of the dataset construction.
Where does textual frequency distillation fit into that pipeline?
Textual frequency distillation, or TFD, public corpora only approximate what a closed model has seen. So the paper asks the model to continue training sentences, collects those generated continuations, and uses them to refine the original frequency estimate. The paper says this step is optional, but it should move the estimate closer to the model's own data distribution.
And what changes for fine-tuning?
For fine-tuning, the paper adds curriculum textual frequency training, or CTFT. Instead of only picking a high-frequency paraphrase, it orders training data from lower frequency to higher frequency within each epoch. The authors argue that rarer expressions are more diverse, so seeing them first and then moving toward more common wording gives a better learning schedule. The paper also gives one equation that ties the story together.
What should I take away from that equation?
It says sentence loss can be decomposed into 3 parts. The first term is negative log sentence frequency, so rarer wording pushes loss upward. The second term is model approximation error, and the third is contextual discrepancy. This matters because the paper is not just saying common wording sounds nicer. It is saying common wording should lower model loss, unless those error terms become large enough to cancel the advantage. Now let us move to the first main result figure.
What result matters most in this chart?
The pattern is consistent across all 3 math reasoning models. DeepSeek v3 rises from 63.5% to 71.5%. GPT-4o rises from 60.70% to 68.70%. And Llama 3.370B Instruct rises from 80.49% to 88.75% when the prompt is rewritten toward higher frequency wording. The intersection law is also important. They show that the high-frequency version keeps the cases that were already correct and mainly adds new correct answers. The next figure isolates the effect of textual frequency distillation.
So what does this ablation actually prove?
It shows that the refined frequency estimate is doing real work. With DeepSeek v3, adding TFD wins on 96.7% of language pairs for BLEU, IT6.7% for CHRF. With GPT-4o Mini, TFD still wins on 100% of language pairs for BLEU and COMET, and on 83.3% for CHRF. So the correction step is not cosmetic. It consistently improves translation quality. This next result asks whether more distilled data keeps helping.
Does the gain keep growing as they add more data?
Yes, the trend lines climb as the amount of distilled data rises from 20% to 60% and then to 100%. Some languages start in the low 70s or high 70s, but by full data, almost every curve reaches the top of the chart. That means the benefit from TFD is not a one-off artifact. Better frequency estimation keeps paying off when the paper gives it more signal. The final figure makes the claim concrete with translation case studies.
Why is this case study more convincing than a single average score?
Because we can see the exact input wording that changed. In both examples, the high frequency input leads to the strongest translation scores. One case reaches VOIU 0.6189, CHRF 51.7009, and COMET about 0.8872, which is better than both the low-frequency input and the original wording. So the paper is not only winning on aggregate metrics, it is also showing concrete sentence pairs where more common wording gives a better output.
What about fine-tuning results beyond prompting?
The fine-tuning story is strong too. Hongyuan, training on the paper's high-frequency partition beats the original ground truth training set, improving BLEU from 4.677 to 5.2466, which is a 12.17% gain. On PHUAT, high-frequency fine-tuning beats low-frequency fine-tuning from 3.9073 to 4.4291, a 13.35% gain. Then CTFT pushes PHUAT from 3.7781 to 4.910 to BLU, a 29.96% improvement. And the paper says that setup gets the best metric in all 8 translation evaluations they report.
If you had to compress the whole paper into one conclusion, what would it be?
The paper argues that wording frequency is a useful control knob for large language models. It gives a reason for that claim through the loss decomposition, turns it into a practical prompting rule with TFL, improves the estimate with TFT, extends it to training with CTFT, and then backs the idea with gains in math reasoning on translation.
So the takeaway is not just that wording matters, but that frequency gives a measurable way to choose better wording on better training order.
That wraps up this paper walkthrough.